Up until now, we haven't been too worried about what the actual sum of the series is. Really, we just want to know if it converges or diverges. And really still that's still going to be the most important thing. Does the series converge or diverge? But down the road, we're actually going to see how accurate some calculations are. And it's good to take a look at this idea of accuracy in the context of these alternating series. So there's something called the alternating series estimation theorem. Okay, we're not going to use this for uh, you know our series or doing our power series later on. We'll use this concept a little bit later, but this idea of how close are we to the actual sum is actually a useful idea. So this is an alternating series, and we know that with an alternating series, we're just going to go back and forth, back and forth. So eventually, we're going to end up at this limit if we do this infinitely. But if we stop at some particular point, we want to know how far are we from the limit, or what is our maximum error from the actual limit. So if I take a look at this sum, I go, there's my first term, second term that's my S2. This here then represents my S3 right there. Okay, so how far off is S3 from the actual limit? Okay, well we want to know. We can't actually say we're exactly some amount off the limit, because then we can actually calculate the limit. We just want to know what is the maximum error. And we can work out the maximum error of this sum S3 by actually taking a look at the next term. Because that next term, we know, if it alternates, we know it's going to go past the limit, and then it's going to come back, but we know that it's going to go past the limit. And we know that this limit can't be anywhere further out here. So what we can then say then is, at S3, our S3 error must be less than the next term, A4. So this is our alternating series estimation theorem, is that we can say that the nth term error must be, the sum of the nth term error must be less than the next sequence term. And so we now have an idea how close are we to the actual sum. And this idea is very useful when we actually want to calculate, we want to see the accuracy of things. We're not going to actually use this to calculate any infinite sums, but this concept comes about later when we want to know how accurate are our calculations. And this idea is very good context to see it in. We can see that, yeah, I know that if this is my S3 value, I know that I can't be any further off than the A4 value. And this becomes a useful idea. Then we have an idea to what degree of accuracy have we gotten our sum up to. And this is very useful. So we can apply this in this context here. So we can say this is my alternating geometric series, and we want to know what the error term must be less than when we calculate S10. Well, if we want to know that, okay, so this is going to look like this. So I'll draw my little number line here. Okay, so I'm going to have, it's going to go start with 0, so n to the power, or sorry, negative 1 to the power 0, so it's going to be 1/2, okay, and then it's going to be 1/4, and it's going to be 1/8, and it's just going to go back and forth, okay, and we're going to have a limit here, and as we go back and forth, our S10 is going to be somewhere about here. Okay, there's our S10. So our S10 is estimated to be about there. As I go back and forth, I want to know what my error has to be less than. And to do that, I'm going to calculate, I'm just going to exaggerate here. This is A11. And we know that from here, and I'm just going to zoom in here, from S10, if we add A11, our next term, we're going to go past our limit. So we know that our limit error must be less than the value of A11. So this is our alternating series error formula. We're just going to say our error at 10, at n equals 10, must be less than A11. Okay? So when I calculate A11, it's got to be the absolute value. My error term for S10 is going to then be, what do I get now? This is going to be 2 to the power, 1 over 2 to the power 11. Okay, so we know that it must be less than that value. It's about, I think it's, if I'm not mistaken, somewhere around 0.005. So we can then look at the error of the first 8 terms of this alternating harmonic series. If I want to know the error of the sum of the first 8 terms, okay, so again, I've got my alternating harmonic series. It's gonna, here's 0 and 1. It's gonna go, 1, 1, 1/2, 1/3, 1/4. Okay, it's just gonna go back and forth. And we know that there's my limit. We happen to know what this limit is. Okay, but the sum of the first 8 terms, okay, S8 essentially, S8 is going to fall, let's say that S8, I'm just going to exaggerate it, it's going to fall somewhere in there. And then my error has to be less than the next term. Okay, so this is A9. So I wrote down 10 here, I should wrote down S8. Okay, so here's where S8 somewhere in there, and I know there's my limit, and my A9 is going to surpass that limit. So what I can say then is my error term for 8 terms must be less than, it's got to be less than my A9 term. Okay, so my error term is going to be less than, when I plug in 9 into here, so it's going to be absolute value, it's got to be less than 1/9. Okay, which is, actually still a significant error because this series actually does not converge very quickly. Okay, so this last one here, we're just going to look at what's the error bounds for S13. So again, the same idea. We're just going to say that the error for S13, it has to be less than A14. Okay, so when we plug it in, the error is going to be less than ln 14 over 14 squared, and we can work out the decimal value, and we can figure out that the error for this sum of this series must be less than that amount after 13 terms. If that's not good enough, I can just keep on going, adding more and more terms. Okay, so this is an error estimation theorem.